Welcome back, everybody. And here we go with our labeling of participants in reactions. Any attacker is a Lewis base. Attacker. Let's go with a color that sticks out. Orange, sure. Lewis base is attacking, and synonymous with Lewis base is nucleophile. Always, without exception. I'm going to save all of the Bronsted until later. Yes, this is a Bronsted reaction, but I'm going to go and do those at the very end. So I can stick with orange right now. This thing's getting attacked by electrons. It must love them. Notice I switched the order because I've remembered this as Lubnu. They always go together, so I made it sound like a name to myself, Lubnu. And Ela sounds like a different name. They always go together, so why don't you have a way to remember them together? So every time an arrow starts, I'm going to call it a Lubnu, the molecule where the arrow starts. Anytime an arrow attacks something, it's going to be an Ela. Every time. This is an attacker. This is being attacked. Don't give me arrows for a rearrangement step because there's no two participants. There's only one. So arrows, labels would be meaningless and confusing. But here, water's the attacker. Lubnu. And this is getting attacked. Ela. Once again, rearrangement. I don't want arrows. I don't want labels. Of course I want arrows. I live for arrows. This thing's being attacked. It's the Ela. This is the attacker. It's a Lubnu. The attacker. The Lubnu. Thing being attacked is an Ela. This is the attacker. Lubnu. This is the thing being attacked. So I have my Lubnus and Elas for every step. You have to have Lubnus and Elas for every step. You put the Bronsted in if the step involves a proton moving from one place to another. I'll do those in hot pink. Here, the proton is moving from this location to the height of the carbon here to make this cation, or to the carbon here to make this cation. Yes, there's new hydrogens here. But the thing is, a hydrogen was attacked. This thing is going to give up the hydrogen to the other molecule. It's going to donate the hydrogen to the other molecule. That is a Bronsted acid as well. The thing taking on the proton is a Bronsted base. Is Bronsted involved going from here to here? The answer is no. These two H's are on the O and they're still on the O. The H's did not move at all. You only made a bond between the O and the carbon. That is a Lewis only reaction, no Bronsted. Underneath it though, this hydrogen's moving from this location, Bronsted acid, it's donating its hydrogen. The thing accepting the hydrogen is a Bronsted base. There's never an excuse to get the Bronsted wrong if you've properly labeled the Lewis. You will never have something be a base in one definition and then an acid with the other. So if it's a Lewis base, then if it's also a Bronsted reactant, it will be a Bronsted base. There's never going to be a case where the A here is contradicted with a B here because there's no molecule that acts like a Lewis base and a Bronsted acid. And okay, I'm trying to help here. If there's an A here and you're going to put Bronsted because a proton's moving, it better be BA. Okay, follow that along. We can stop even thinking about it now that I gave you that trick. How do you know it's a Bronsted over here? Because a hydrogen's moving. Lewis base, when it's a Bronsted, is always a Bronsted base too. And a Lewis acid will be a Bronsted acid. I am not going to add Bronsted to this one or this one. Try that on a test. You will lose a 1/4 point for each label because they don't belong on a reaction where hydrogen is not going from one place to another. Same story here, but over here, our final occurrence, protons moving away from this part and towards this part. And you'll notice every time we put a Bronsted, the second part matches the first in the Lewis part. Acid matches acid. Base matches base. Acid matches acid. So there's your labels, and all we have to do is explain this right here. And there's two possible explanations depending on the reaction you're talking about. Now, in this one, it's not a hyperconjugation argument. And please don't do your explanation based on the products at all. The explanation must be talking about the intermediate that's the least stable, because that's the one involved in the rate determining step. And yes, all of these reactions where there's carbocations, their formation is the rate determining step. We need to pick the one that forms fastest. And this one would form very slowly. It's primary. We don't like that. Secondary is going to be a lot faster. But secondary that rearranges to secondary with no ring strain or minimal ring strain. Your explanation needs to be down here and talking about why that's the best cation. And this is part B. My explanation has to talk about the cation from whence this came. So carbocation there. The cation, this, oh, lost my pen. This C plus, you don't even have to write carbocation, you can write C plus, has much less angle and torsional strain than the other C pluses. So that goes to say it'll form faster. So you'll form more of it during the same amount of time, and you will make more of the product that comes from it. But you need to talk to me about the carbocations, okay? And that brings to a close that big question. And point counts for the labeling, well, they're a 1/2 point each label. So if I go for 6, that's 3, and then 5, and then 8, and then let's see. It's going to be tricky here. I forgot where I left off to. 3, 5, 8, 10, 13, 16 points worth of labels in a question that's worth, let's see, this is 9 points here and 4 more is 13. Yeah, I told you more than half the points here. This is almost a 30-point question. And yes, yours will be almost a 30-point question on your test as well. So I hope you found that useful. We don't usually start with test questions, but I thought it was appropriate there. We're going to begin the end of chapter 6 now, and we'll take till the end of today to finish chapter 6. We're going to review hydration reactions because we've looked at a couple of them. Actually, we've looked at 3 hydration reactions in this chapter so far. When we add H on one side of an alkene and OH on the other. We did a reaction where we made what's called a Markovnikov alcohol here. The more electronegative O on the more substituted carbon, the less electronegative H on the less substituted carbon. We reversed the script when we did hydroboration and oxidation. We put the more electronegative O on the less substituted carbon. Yes, that's a primary carbon. That is an anti-Markovnikov reaction, but they're both hydration reactions because the new stuff is water. I didn't include it here, but the oxymercuration, demercuration would give the same result as this first one. It's a 2-step process with mercury 2 acetate and water in the first step and sodium borohydride in the second step. You want to review that. But for the discussion here, it's the same result as this product here. And we're talking about redox here. So we don't have to have it separate. It belongs here. HBr, we saw that was our first reaction in the chapter. We get a Markovnikov alkyl bromide with the more electronegative Br here, less electronegative H here, more substituted, less substituted. And then we did bromination. Bromination, which is halogenation, or halogenation in the presence of water. And then we got a vicinal halohydrin alcohol. And they're both Markovnikov. Well, this one's Markovnikov. This one I can't tell Markovnikov, anti-Markovnikov, because the atoms that are new have the same electronegativity. We don't say there's regioselectivity there at all. Okay, at the top of the page, all the reactions up here and here, they're not considered redox, even though I discuss redox for all of them. So let me remind you that an atom becomes reduced if electrons move closer to it. So if you're a carbon atom that used to have a bond from carbon to carbon and you replaced that, yes, the bond from carbon to carbon, the second bond is gone and replaced with a bond to a less electronegative hydrogen, then the electrons in this bond are closer to carbon than they were in the pi bond before. Moving electrons closer is reduction. So that carbon that I labeled number 1 got reduced, and you can do oxidation states to prove it. Oxidation states of carbon number 1, carbon 1 went from, oh, is that a typo in the book? Yeah, it is. Oxidation state of carbon number, oh, at the end it's -3. Sorry, I'm not even reading my own thing. Oxidation state at the beginning is -2. Correct, no mistakes. At the end, carbon is 3 bonds to less electronegative H, -3. So we went from -2 to -3. We went down by 1. That's called reduction. And we already said reduction because we conceptualized it. The carbon here has 1 bond to a less electronegative H and 3 bonds to the same electronegativity, -1. At the end, -1 for the H and +1 for the O. You end at 0. You went from -1 to 0. You went up by 1. Conceptually, you traded a bond from carbon to carbon for a bond from carbon to a more electronegative oxygen. The electrons moved away. Moving electrons away is oxidation. Meow. Moving electrons away. Oxidation. Got it. So in the same molecule, we had the same amount of reduction. Carbon 1 went down by 1 oxidation state, and carbon 2 went up by the same amount in an oxidation reaction. So the net result is no change in oxidation state for the overall molecule. So we say this is not a redox. Got it. So hydration reactions are not redox. We did the same story here, except atom number 1 got oxidized and atom number 2 got reduced, but they got oxidized and reduced by the same amounts. And they cancel again. HBr, same story. Br is more electronegative than carbon. So this got oxidized. H is less electronegative than carbon. This got reduced by the same amount. The other one got oxidized. It's not redox. When do we have redox? Well, we moved on to the reaction with the halogens. Both carbons went from a lower number to a higher number. That's oxidation by 1 and oxidation by 1 here. They both underwent oxidation. We say this reaction is an oxidation reaction, and our inorganic chemistry friends have a fit. They say you can't have an oxidation without a reduction, and they're right. But us organic chemists, we're notorious. In fact, it even says right here, we're notorious for describing what happens only to our organic molecule. In my organic molecule, both the carbons got oxidized, so I call this an oxidation reaction. Now, I realize bromine went from an oxidation state of 0 to -1, and my inorganic chemistry friends, I'm going to tell them, yeah, Br got reduced. At the same time, carbon got oxidized. So you guys are right, but I'm only talking about my organic molecule. Oxidation. Same story here because chlorine and oxygen are both more electronegative than carbon as well. And we call that an oxidation reaction. And then finally, we're going to learn some new reactions, the final 3 reactions for this chapter. And the good news is you don't have to learn the mechanisms except for small parts of this first one. And these 2 reactions here are called oxidation reactions for the same reasoning we gave before. Carbon went from -2 to -1, got oxidized. Carbon here went from -1 to 0, it got oxidized. 2 bonds to more electronegative O were created, that's oxidation. So forming a vicinal dihydroxyl compound, also known as a vicinal diol, not a vicinal diol, but a vicinal diol. They're also called glycols. So we have to learn these things. Vicinal diols are called glycols. And this particular one here you can find in a couple locations. This would be environmentally friendly antifreeze or in your ice cream. Some ice creams use that. Some ice creams have this added to them as an emulsifier, so the cream stays with the ice and they don't separate. Anyway, that's a molecular recognition discussion, and we don't even do that in this semester. Ozone. You've heard of ozone. Where is ozone found? Where can you go and find some ozone? Well, you can find it in our upper atmosphere. It's up there protecting us from ultraviolet radiation. It's doing a good job, much better than it was doing 30 years ago when we were depleting it. And that's an example of good regulation worldwide. Anyway, we'll talk about that next week. Good regulation. Ozone can be used to pop open alkenes and cut them. The suffix here means cut, lysis. And you'll see we are lysing right here, cutting. And you get 2 new bonds to O, replacing the 2 bonds to carbon. So the oxidation state goes up by 2, doesn't it? From -2 to 0 and from -1 to +1. So this is even more extensive oxidation, isn't it? So in ozonolysis, you're going to learn how to easily predict the products. It's as simple as getting an eraser out and erasing the pi and then just sticking an O on each side and you got the pi back. Yeah. And where's the third O of ozone go? It ends up with the sulfur in this chemical here. This is a side product. That's why it showed up a little smaller. And it's an example of oxidation, and we haven't seen an example of reduction. And reduction is very commonly done with hydrogen in organic chemistry. And you take your pi bond and you replace this pi between the two carbons that have the same electronegativity in that bond, and you replace it with a bond to a less electronegative H. So this carbon got reduced, and a less electronegative H here. So the other carbon got reduced by the same amount, -1. Both are reductions. So we call that a reduction reaction. And that is fair enough. So what are we going to be responsible for in this reaction right here? I'll tell you. This reaction right here. Bisphenol dihydroxylation. There's a lot of good stuff going on there. And what we have is a molecule OSO4, and it looks like this. Yeah, it's not doing pink. Now, lowercase, very important here. That is not the same thing. That's oxygen. Oh, oxygen, and this other one is sulfur. OS over here is osmium. So do not confuse lowercase and uppercase in a chemistry class unless you want your teacher to just put a lot of red marks on your test. Osmium tetroxide is probably the highest oxidation state you've ever seen. This name is very, that's not a good name, but it's its common name. I don't like it. You've mixed up two styles of nomenclature. You're not supposed to use prefixes like tetra for ionic compounds, and you have done just that. You're supposed to use oxidation states, aren't you? So its more appropriate name is osmium with 8 bonds to a more electronegative oxygen, to more electronegative oxygens. That's supposed to be a U. It looks terrible. Is osmium plus 8. And the anion is called oxide. That's your normal O2 minus ion. That is the more appropriate name, and I just don't like the way my U looks. Can I get a U? Really struggling. I'm going to have to resort to typing one. This looks like a U for sure now. Okay, that was silly. I'm sorry. Osmium 8 oxide. When you're done, you also have osmium 8 oxide. What? That doesn't make sense at all. But with the protocol we're using here, you're going to have 2 original oxygens from before, and these new oxygens, which come from here. I don't know. That's not doing it for me. And the mechanism shows us why this happens. Now, every mechanism we've done so far, the pi electrons have attacked a positive atom. So why am I going to attack an oxygen ever? Oxygen bonded to osmium is going to be a normal O with a negative, right? Like an ionic compound. But OS plus 8, osmium with an oxidation state of 8, is highly oxidized. This osmium is saying, please give me electrons like this. And oxygen's saying, I'm not going to do that. I am not going to let that happen. I am more electronegative than you, even with your plus 8-ness. But that arrow will happen if the pi electrons are attacking oxygen. Oxygen's distracted, says, oh, okay, you've got replacement electrons for me. I'll give you some electrons. And why did I choose to go this direction instead of like the other direction around? It's because these two arrows would generate a carbocation. And which carbon do you prefer for a carbocation of these two? Your answer is this one because it's secondary. I do not want a carbocation here. But we're never going to see a cation anyway because the pi electrons in this bond end up attached to the carbon that would be the more stable carbocation. I hope that sounds familiar. If you look back at all 4 segments last week, each one of them involves me saying, bring the electrons back to the more substituted carbon. Each segment last week on Wednesday. So am I changing? No. So don't bring the electrons back to the least substituted carbon. It's spending no time with a positive charge. And what would you guess the intermediate looks like here? It's got the black parts here. And we have new bonds here and here. We have oxygens attached to each of those bonds. My green arrow's too big. Coming to an O little s. We didn't touch these. If you want to be picky, we got a new lone pair on the osmium. That's how it got reduced. This osmium's a lot happier than the original. This is only osmium plus 6 now. You lowered his oxidation state to a more reasonable plus 6, which is still incredibly high, but it is not plus 8. And this is called an Osmate Ester. Species that look like acids, whose H's have been replaced by carbons from ic acids in particular, are called esters. And this species here, where we have the H's on it, is called osmic acid. That's an aside. You don't see osmic acid in this reaction. But esters are named after acids. So I replaced each of these H's with carbons. You want to get real picky, it should be called an osmate diester, shouldn't it? But they don't do that. So you're responsible for these arrows. Responsible for these 3 arrows. And this intermediate. So you should be able to provide the intermediate to me on a test if I ask for it, and provide the arrows that make the intermediate if I ask for it. And make sure you know those lone pairs and not dot, dot, dots. Dot, dot, dot here is continuation of a sentence. Okay. You're responsible for the chemical that will break this down to give these products. So if that was a big blank, you'd be copying this down. And that's not a carboxylic acid. Even if you think it's a carboxylic acid here, you have to rethink your position. This carbon has 3 bonds to methyls, and it has a 4th bond, at least a 4th bond to oxygen. It has no room for a 5th bond being a pi bond to oxygen. And then another bond to oxygen would be 6, which would be totally ridiculous. This is a tert-butyl attached to a peroxide, and that's this, tert-butyl hydrogen peroxide. And this O here, if you're curious, it's the one here that ends up attached to the osmium to regenerate the catalyst. I let it out of the bag. This chemical makes OSO4 into a catalyst, doesn't it? And for those of you who are concerned about side products and things like that, you're going to get this side product, tert-butyl alcohol. You're not responsible for showing that or knowing that. So there'd be 3 products there. This is not a product, it's a catalyst. And this is just a sad aside. Don't make me sad when I'm grading your tests. Lowercase s. All right, so we can generate vicinal diols from alkenes. That's a very important take-home message. Alkene becomes vicinal diol. One important feature we have not explored yet is the stereoselectivity. You can't talk to me about regioselectivity, not with this product. Both groups are identical. You don't talk to me about regioselectivity. Stereoselectivity, let's talk. Our favorite alkene. So if I give you OSO4 and tert-butyl OOH and asked you for a product, your answer needs to have a vicinal diol. I'll give you a partial credit answer. Partial credit, half credit. You get half credit for that answer. You put the groups on the right spots. You put the right groups on the right spots, but you did not indicate that you know what happens when all of the bonds happen simultaneously, that they end up on the same side of the ring. There's no triangle with a backside attack in this mechanism. This is from Sin Addition. From Sin Addition in the, I'm going to label that step with a telephone pole. And here's the telephone pole step. Why Sin Addition? Why do they happen on the same side? Because they happen at the same time. All 3, well, these 2 new bonds happen at the same time. So without a ring, I could have showed wedge, wedge, or dash, dash, but I didn't have to without a ring. With the ring, make sure they stay on the same side. And yes, you are correct. You generate 50-50 mix of that, and it's an enantiomer. I don't need to see that on the test. Just draw this one on the test for full credit. I don't need to see all this extra information. Unless you want to show off, that's fine. And that is a good spot to stop this segment, and I will see you very soon.